Our objective in 5.2 is to use the log rule for integration of rational functions and trig functions. Remember last time we did the derivative of the natural log of x. What did we get? 1 over x. When we did the derivative with respect to x of negative x, well, we had to consider that we have more than just x, so we used our chain rule. Well, what's our chain rule? D dx of natural log of u prime over u. So the derivative of our inside function u prime is -1 over u, negative x. Simplify that into 1 over x. Notice that when we had natural log of x, we got 1 over x. When we had natural log of negative x, we got 1 over x. So whether it was positive x or negative x, we got the same derivative. Well, the natural log of the absolute value of x can be split up into the piecewise function natural log of x when x is greater than 0. Remember, we can only plug in positive x values into the natural log function, or the natural log of negative x, but that's when x is a negative number. So that again, we're only taking the natural log of positive numbers. Well, this means that when we do the derivative of the natural log of the absolute value of x, so the derivative of the natural log of the absolute value of x is, in pieces, 1 over x when x is greater than 0, still 1 over x, this is where I'm looking, here and here, when x is less than 0. So don't really need it in this format. We wrote last time the derivative of the natural log of the absolute value of x is 1 over x. No matter what x is, positive or negative, that is what we're getting. So today we're going backwards. Today we're starting with a rational function and asking, what is the antiderivative? So there you have it. If we are doing the antiderivative of 1 over x with respect to x, we get, well, go backwards. What did we take the derivative of to get here? The natural log of the absolute value of x. Of course, there could have been a constant plus a constant. Let's write that down and let's use that. So I want to integrate today rational functions such as 1 over x with respect to x. That's the natural log of the absolute value of x plus c. But we know it's not always just going to be 1 over x. It could be a more complicated rational function. So really we're talking about 1 over u, where u is a more complicated function with respect to u is the natural log of the absolute value of u plus c. This is the same rule, it's just thinking of it with u substitution is usually going to be what we're trying to think of. Let's take a look at some examples. Evaluate the following integrals. Well, first of all, I'm thinking to myself, I have a rational function. Now, you may be inclined to simplify or rewrite and use our power rule. Well, I just want to show you quickly what it looks like when x is to the power 1 in the denominator. If we rewrote this as 3x to the negative 1, and we tried to use our power rule, we add 1 to the exponent, we get 0. We divide by the new exponent. Well, what happens when you divide by 0? That's right, you can't do that. So we're not going to do that. We're not going to rewrite it when x, or the denominator, is to the power of 1. Instead, we're going to think, well, what function has a derivative of something over x? That's our natural log function. We need to remember that when x is to the power of 1, that's our natural log function. Okay, so let's approach it that way. We still want to rewrite it. We want to rewrite it such that we see 1 over x with respect to x. That's 3 is just a constant multiple, so we're going to pull it out. So 3 times the integral of 1 over x with respect to x. So we'll do this part with the 3 outside using our property. We've got the 3. The antiderivative of 1 over x is natural log of the absolute value of x. Really important, we remember the absolute value. And of course, plus c. So this is a good answer. We could say we're done here. But remember, with logs, there's a variety of ways that you could see the answer. You could see the answer as natural log of the absolute value of x cubed plus c. Because you have our coefficient, the property says we can write it as the exponent of what's in the natural log. Let's take a look at another example, a definite integral. Again, we can rewrite this one, and we should, with the 6 pulled out, 1 over x dx. I threw some limits in here to practice doing a definite integral so that you could see there's a lot of things to do in simplifying, and in multiple choice, you really need to recognize and practice those situations. So we have 6, the antiderivative of 1 over x, natural log of the absolute value of x. I could say plus c, but it's a waste of effort because I know it's going to subtract away. We put our brackets 1 to e. So I'm going to bracket this side too just because we took the 6 out. So I have the 6 out, plug in the upper limit first. Natural log of the absolute value of e minus natural log of the absolute value of 1. Well, really at this point, these absolute values are not necessary because e is a positive number already, 1 is a positive number already, but it's good to stay in the habit of remembering to write the absolute value. So then I have to think to myself, well, what is the natural log of e? Remember the 2 points that you have to know on the natural log function? Well, this is one of them. Natural log of e is 1, and the natural log of 1 is 0. Remember those 2 points. You have to know those 2 points. Okay, so the natural log of e is 1, the natural log of 1 is 0, and 6 multiplier. So 6 times 1 minus 0 is 6. If you left your answer like this, not such a good practice because in a multiple choice, usually you're going to see it like this. So let's try to get down that simple. Let's look at a few situations that are a little bit more complicated. So here's another rational function, and the denominator is not just x. So we think to ourselves, u substitution. If it's not just x, but the variable is there, let's call that denominator the u. So if u is x plus 2, remember the next step? The derivative also has to be found in the integral, or we need to manipulate it so that it's there. The derivative is 1, and then I solve for dx. dx is, in this case, just du. So I do some substitution, and my integral turns into 1 over u. dx is just du, so times du. And now this looks like my 1 over x dx situation. So I do the antiderivative, the natural log of the absolute value of u, plus c. But we started with x's, so we end with x's. U is x plus 2, so one last step, natural log of absolute value of x plus 2 plus c. Starting to get the idea? Let's look at another scenario. I have another rational function, but it's not just 1 over x or just 1 over x plus 2. I've got a little bit more in here. Well, let's take our time and really think back to where this came from, this 1 over u. If I'm thinking of doing the derivative of the natural log of the absolute value of u. Remember that it's u prime over u, the derivative of the inside over the inside. Remember that? Okay. So when we're thinking backwards and starting with a rational function, well, think to yourself, I'm starting with this side, where what's on top is the derivative of what's on the bottom. So when we're going backwards, ask yourself, is what's on top the derivative of what's on the bottom? Well, this one's pretty close. What's on the bottom, if I take the derivative, I get 2x. Well, the top is not 2x, but 5 is the only thing different here. And a simple constant multiple can be dealt with quite easily. So let's see the process for working when we notice that the top is very close to the derivative of the denominator. Let's say the denominator is our u. So very similarly to how we did it over here. U is 1 plus x squared. What is du dx? Because we know we need the derivative in our integral. It is 2x. Solve for dx, we get du over 2x. Do our substitution, dx is du over 2x. Rewrite our integral. Integral of 5x still is there, over u, the denominator's u. Dx became du over 2x. So our x's cancel out because, like we said, we had part of the derivative up there, but the 5 and the 2. Well, remember what we can do with those? Constant multiples get pulled out. So 5 over 2 out of our integral with 1 over u du left over. Now this is our natural log antiderivative. 5 over 2, natural log of absolute value of u plus c. And then, of course, we want it in terms of x, not u. So 5 over 2, natural log of absolute value of 1 plus x squared plus c. So again, let's consider the ways we could see our answer. This, a fantastic way. Another way you could see it in case it's multiple choice. Well, x squared will always be positive. So positive plus 1 will always be positive. So perhaps it's shown without absolute value because this stuff will always be positive. Still correct. One is not better than the other, just recognize that both are good possibilities. Well, what is something else that we could see? 5 halves could be the exponent. So perhaps, and I'm running out of room because there's so many options here, perhaps it could say the natural log of 1 plus x squared to the 5 halves plus c. Perhaps instead of to the 5 halves, they wrote this with the square root, 1 plus x squared, and then to the 5th plus c. So many options with natural log. Be careful when you're looking at possible choices. So here's another one where we say, I have a rational function. The denominator looks like if I take the derivative, it's 2x, which is kind of like the numerator, but this one's a little different because the numerator has a variety of terms. Now, just because now when we're doing rational function antiderivatives, we can use natural log, doesn't mean that we have to use natural log. These are rational functions that we can't make not rational functions. What I mean is, when we've seen problems like this before, we could make these kind not quotients anymore. How do we do that? Well, I'm not going to put equals there because I'm not going to deal with the integral right now. I'm just going to look at the expression x minus 4 over x squared. I can divide x by x squared and 4 by x squared. I'm dividing it into the numerator, this one term, into the numerator. So this becomes x to the negative 1 minus 4x to the negative 2. Now, I really shouldn't have written that as x to the negative 1 because I know that power rule won't work for that guy. So I'm going to leave this one as 1 over x. When it's 1 over x, I have to use my natural log. So let's rewrite our integral from 1 to 2 of, I'm rewriting 1 over x minus 4x to the negative 2 with respect to x. What I got when I divided. So what did we do here? What did we do here? We divided. We split up the numerator by dividing. Okay, divide. Then we can do the antiderivative. So the antiderivative of this part is natural log of absolute value of x minus, now we'll use our power rule, add 1 to the exponent, we get x to the negative 1, divide by the new exponent, plus c, don't need it because I have a definite integral, 1 to 2. Now we can, I'd simplify that first. I'd like to do that always. I don't like the negative exponent. So minus negative is plus 4 over x from 1 to 2. Now we'll plug in our upper limit first. So the natural log of 2, I don't need the absolute values because 2 is positive, plus 4 over 2. First guy, minus, plug in 1, the lower limit. Natural log of 1, again 1 is positive, so I don't need the absolute values, plus 4 over 1. Simplify, please. Natural log of 2 plus 2 minus natural log of 1 is 0 plus 4. So again, a little bit more simplifying. Natural log of 2 plus 2 minus 4 gives natural log of 2 minus 2. Looks good. Let's take this a step further. Well, often we've asked ourselves when we have a rational function, u prime over u could be what we're looking at. So if our denominator were u, what's the derivative of it? Do we see it in the numerator? Quite the contrary. The denominator has a derivative of 1, and this is a lot more than 1 in the numerator. Well, remember the problem that we were just on. What did we do? We divided the denominator into the numerator. So what can we do here? That's right. We can divide the denominator into the numerator. So this is another example where we want to divide to break it up, the denominator into the numerator. But it's not as simple of a division as the other one. In this one, we're going to have to either use long division or synthetic division. I want to show long division because you can't always use synthetic division. Hopefully you remember synthetic division, but it's not always possible. So I'm going to practice with the long division way just because that will always work. Synthetic division won't always work. So let's see what we do. Dividing, we look at the first terms. X goes into 2x squared, 2x times. How do I know that? Because 2x times x makes 2x squared. 2x times x. 2x times negative 2 makes negative 4x. Then what do I have to do? Subtract. So minus, subtracting a negative makes plus. Let's see what's left over. Those cancel out. That makes 11x, bring down minus 3. X into 11x makes positive 11. How do I know that? Because 11 times x is 11x. 11 times negative 2, negative 22. Now I subtract. Minus a negative is plus. Those are gone. This makes 19, and 19 can't be divided by x. So what does that mean for my new integral? Instead of this, I have 2x plus 11 plus the remainder of 19 over the divisor of x minus 2. How does this help us? Well, this, easy antiderivative, x squared. This, easy antiderivative, 11x. This, not as easy antiderivative, but one that we've practiced on the other problems. If I want to do this antiderivative, I just have to do a u substitution. Call u x minus 2. du dx is 1. Therefore, dx is du. Do a little substitution here. Think of this as 19. Probably pulled out of the integral would even be nicer. Let's write it that way. 19 times the integral of 1 over u. dx becomes du. And there's my natural log. 19 natural log of absolute value of u plus c, or 19 natural log of absolute value of x minus 2 plus c. Let's put it all together. Don't forget about this stuff that was in the front. X squared plus 11x plus 19 natural log of the absolute value of x minus 2 plus c. There we go.